So Ohm's law is a measure, or ohms is a measure of resistance, which we are talking about in terms of variable capital R, right? And we've actually already explored Ohm's law, we just didn't give it a name, right? And so Ohm's law is a relationship between a voltage difference, like for a battery or a capacitor or a power source, the current that is flowing out of that power source, and the resistance of the material that it's moving through, right? We talked about different kinds of wires and different properties of wires affecting their resistance. What are some things that affect the resistance of a wire? Yeah, the length and the area. A-R. Oh, yeah, I can't spell. And the area of that wire. Ohm's law is something that is used over and over and over again by people in the technical fields. And so aviation maintenance, I think they spend a whole semester on Ohm's law and just getting that into the maintenance guys' heads. This goes for automotive technicians, any kind of stereo installers, the people who set up equipment at concerts to make sure that they're not overloading circuits, and then electricians and electrical engineers when they're designing buildings overall. What happens when you overload a circuit? It blows, yeah, right? And so you have to go into the, what is that thing called? Control board? Breaker, thank you. You have to go into the breaker and flip the switch and reset that circuit, right? Because if you're drawing too much current out of it, then it's not able to support all of those devices and everything shuts down. What are some things we know that draw a lot of current and can flip breakers? Heaters, absolutely. I tripped half of Kramer one day with my little space heater. And also poor circuitry setup in there. What else can flip breakers because it draws a lot of current? ACs, yeah, heaters, ACs, what else? Refrigerators, yeah. Hair dryers are really bad because they're like a heater, right, but condensed. And anytime you generally just plug a lot of junk into one outlet, and so if you're one of those people that has like octopus cords coming out of one outlet, then you tend to overload the circuit and flip the breaker. And so voltage, remember, is the potential difference, and you can think of this as like a pressure, right? And so with that water analogy, the voltage difference, a very high voltage difference is a very high kind of pushing pressure, right? Very high voltages can go through very high resistance materials because they have that push. Very low voltages can't go through high resistance materials because they don't have the strength, they don't have that push. Where do we get voltage differences? We've learned, I think, 2 ways so far. Delta V. You're right. I'm asking, you're right about the calculation of that. But what are 2 devices that can give me a voltage difference that we've talked about? And these are just common everyday, well, one's not so common. Right, and so I can get a voltage difference from a battery. What is the advantage to getting my voltage difference from a battery? Yeah, they release slowly. What is that other device that I can get a voltage difference from, but it unloads a voltage difference very, very quickly? Yeah, a capacitor. Particularly, we've talked about parallel plate capacitors. Today we're also going to talk about the voltage that we can get out of a wall outlet. Typically a wall outlet, and this is something you can put on your formula sheet if you want, or you can refer to it in your book. A typical household outlet is 120 volts. Right, and we'll use that in our calculations today. Battery is typically like 1.5 volts. Parallel plate capacitors have a have a pretty big range, but comparable to batteries. Right. Current refers to the quantity or volume of an electrical flow. What is the unit for current? I've asked you this, but we'll review. Ooh, what is it? Yeah, the symbol is I, right, in our formulas. Coulombs per second, yeah, but how do we simplify that? Yeah, we call it amps. And if something has a high amperage, what does that indicate to me about the charge flowing through it? It's fast, right? There's a lot of charge flowing through it. And if something has a low amperage, what does that indicate to me about the charge flowing through it? Yeah, it's slower. There's not as much charge flowing through it. Do you guys remember what amount of current is harmful to humans? Yeah, 1 amp, right, is extremely harmful to humans. At microamps, you begin to feel muscle spasms and twitches. Nice job. And then resistance is something that kind of pushes back against that voltage difference and makes it a little harder for current to flow. Resistance is measured in ohms. What is that property of certain materials that relates to resistance? Yeah, it's a constant. What do we call it, though? It's measured in ohm meters. Yeah, the resistivity of materials. Can you give me an example of something that has a high resistivity? Glass, right? Something that has an example of a low resistivity. We use it in our wires. Copper, yeah. And so this is just kind of a summary of those things that we just went over, right? Current gives, we measure it in the variable I. The actual unit of measurement is the amps, which we abbreviate with an A. Voltage, I'm going to scratch that one out. We use the symbol V. It's measured in volts, and again, that symbol V. Resistance is that capital R in your formulas. It's measured in ohms, and Greek letter omega for that. Y'all feeling okay about those 3 things? Okay, that's all review from last time. In general, assuming that the resistance doesn't change, right? As voltage increases, current increases. Make sense? Okay, that's old material too. As voltage decreases, current decreases. However, once I add resistors to that circuit, right? Once the resistance goes up, current goes down. And we just saw that with our resistor, right? As I increase the resistance, that current on the galvanometer goes down, down, down. As resistance decreases, current increases. Right? There are materials that do obey Ohm's law, and there are materials that don't obey Ohm's law. Ohm's law isn't like law of conservation of energy in that it is always, always, always true. Ohm's law is a little bit different, and so we have what we call ohmic and non-ohmic materials, right? Ohmic materials are things that follow Ohm's law. When I look at a graph of current and voltage, there's always a linear relationship between those two in an ohmic material. In a non-ohmic material, I have some kind of a non-linear relationship between those two if I'm looking at a graph. Most resistors and metal wires, or what we would call a load, anything that does work with electricity, is an ohmic material. And so light bulbs, computers, headphones, speakers, you name it, those are ohmic materials, typically. What's more important is for you to remember the things that are non-ohmic, because there's really only 3 that don't abide by Ohm's law. And those 3 are batteries, semiconductors, and capacitors. And you already know that batteries and capacitors are very similar. Semiconductors have a variable resistance depending on the amount of current that is going through them, and that's why they don't follow Ohm's law. So they have a relationship that looks a lot more like this, right? As I increase the current, the voltage difference changes as well. Right. A good example of resistors in your daily lives are anything that heats up. So heaters, toasters, hair dryers, ovens do this, the burners on top of your stove do this. And so we've got some kind of conductive material through which we send electricity, and as we send that electricity through, what happens to that material? It heats up, right? Why does that material heat up if I send electricity through it? Kind of. It doesn't want the electricity. Imagine if I'm trying to push something, right? What causes heat to form in that relationship when I'm pushing something? Friction, right? This is friction on an ionic and electron level, right? And so that causes heat to form. As the nichrome wire heats up, the resistance increases for this toaster, right? And as resistance increases, so does the heat of the toaster, because it's kind of pushing back, you could imagine, on those electrons, and you get some friction there. As that resistance increases, right, when the toaster heats up, what happens to the current? So I've got some kind of a power supply. We'll say this is a battery-powered toaster. Yeah. The current on the other side of that, right, and we represent like that, decreases. And so the current here, coming out of the toaster, is less than the current going into the toaster because of the resistance. Make sense? We're doing okay? Okay, good deal. What happens to the voltage difference across the resistor? And so the voltage here versus the voltage here. Not the same. If current is decreasing, what is it? Yeah, it decreases. There's what we call a voltage drop across the resistor. And so if I were to graph this, right, the voltage, and I've got my resistor here, I would have kind of a very high voltage. It would drop, and then whatever comes out on the other side of that is a much lower voltage. And so let's use Ohm's law, right, to calculate. I've got a battery voltage of 12 volts. We've got a resistance of 2 ohms. What is the current in amps? There isn't. Batteries don't follow Ohm's law because the delta V for a battery is attributed to chemical energy, not resistivity. Right, and so when I'm talking about voltage difference across a battery, that's non-ohmic. But what I'm talking about here is I've got some kind of battery, and what is this? It doesn't even say. We'll just call it some kind of a device, light bulb, whatever you want to use. I'm talking, this has a 12 volt difference, right? And so I initially start with 12 volts. What's the current flowing through on the other side? I could calculate a voltage difference here, but we're getting there. So hold on to that thought. This is just really straightforward Ohm's law. So what is Ohm's law? And so what is delta V? 12 volts. What is the resistance? 2 ohms. Which gives me a current of what? 6 what? Amps. Not bad. Right? Voltage is 12 volts, current is 4 amps. What is the resistance? Mm-hmm. So I get 12 volts over, and then 4 amps over the R, right? And so I get a resistance of 3 what? Ohms. Ohm's law is easy. Don't overcomplicate it. Right? And so the voltage across a resistor. We said that the voltage here, right, before it hits that resistor is higher than the voltage coming out. The current here is higher than the current coming out of that resistor. And we can use Ohm's law to mathematically kind of support that idea. We know that there's a voltage drop, thus there's a current drop across the resistor. Even though when we first introduced the idea of resistance, we talked about wires having a resistance based on their length and their area. Wires do have a resistance in a circuit based on their length and their area, but because wires are generally such good conductors, their resistance is pretty negligible when you put it up against something like a light bulb. And so for our purposes, we assume, right, when we're talking about currents, that those wires have no resistance. Because it's practically zero when you compare it to the volume of resistance supplied by a resistor. And so when I give you a circuit, you don't need to be thinking, okay, well, what's the diameter of this wire? How can I find the area? How long is that wire, et cetera, et cetera. I'm not going to hold you to that, right? From here on out, resistors, specifically resistors, are the only thing that's going to decrease that voltage, not the length of the wire you're using or anything. Real world resistors look like this. Have you guys ever opened up a circuit board of any kind and seen these? Yeah. Little resistors like this are put into circuit boards. Why would we want to put resistors into a circuit board or any device? Yeah, to control the current that's going to that device, right? Because if I overload a device on current, what's going to happen? It's going to flip that device, right? It'll shut that device down. Or in the case of a house, it'll flip a breaker. It'll shut that device down. And so resistors are used to control the amount of current and kind of where it's going in that circuit. The other reason technical people are drilled on Ohm's law is they're responsible for constructing these circuits. And the banding on resistors is a code for their resistance and how they act in that circuit. I'm not going to teach you guys the code or hold you to it, right? I just want you to know what resistors do. I will give you the resistance. I'm not going to expect you to read bands on a resistor. If you do go into electrical engineering, become an electrician, mechanic, anything like that, then yes, you will have to learn these because it's your job to construct those circuits. We can talk about the electric field within a resistor. Even though there is a kind of voltage difference, we're going to assume that the electric field is constant within that, and that it doesn't change. And so you can kind of treat it like a parallel plate capacitor. That's a uniform field within there. If I wanted to calculate that, it would be the voltage drop across the resistor, right? Just like when we had the parallel plate capacitor, and we talk about the voltage drop across that. And instead of distance between the plates, we now talk about length of the resistor. Right. And so what happens, by just looking at this, what happens to the electric field when I increase the length of a resistor? It goes down. So if I had a voltage drop of 2 over a distance of 2 versus a voltage drop of 2 over a distance of 4, right? It goes down. And that makes sense with what we know. The current is decreasing. If the current is decreasing, the strength of the electric field is decreasing as well. All right. We use resistors to decrease or increase the voltage applied to something that's using power and electricity. There's a couple of types of resistors that I may throw in these words on an exam, and I would expect you to know what they are. Not most, but a lot of our automatic devices depend on resistors to regulate them. And so a thermistor is any kind of resistor that turns on or off based on a temperature. What are some devices that you know of that turn on and off based on a temperature? Your iPhones. Yeah. What else? Hair curling iron. What else? A really important one in your homes. Thermostats. Yeah. Heaters. Right? And so when the temperature gets below or above a certain level, that resistor suddenly decreases its resistance, allows current to flow, and turns on your air conditioner. Okay? A photostor is a resistor that senses light. And your book gives a really good example that I like, which is night lights, right? When you turn out the lights in a room, it senses that. It decreases its resistance to allow current to flow, which turns that light on, right? When it senses that lights are on, it increases its resistance, and the light is off. And so that's how they're kind of automatic, like that. These are what we would call variable resistors. Which means they can change their resistance. Which is pretty cool. We do have constant resistors that have a constant resistance. And those are the ones that we use in little circuit boards, the ones with bands. Those are constant, right? What is this one that I have set up in the back of the room? Variable or constant? Constant? Its resistance is always the same? It's variable. How do I vary the resistance on that? Yeah, changing the length, right? And then the value of a resistor is marked using colored rings on those little tiny circuit board ones. And so, taking in that information in Ohm's law, I want you guys to actually try one of the critical thinking questions that's embedded in your text, page 727. Stop and think, number 22.4. And then we'll do a couple of calculation problems as well. And so that little diagram has a simple circuit, right, with two batteries, a wire, and then what we would call a load, something that is using that electricity. Where is electricity flowing out of those batteries? On the top or the bottom in that picture? The top. How did you know? Because that's the positive terminal. Good. And so we know electricity is flowing in this direction. When we looked at parallel plate capacitors, which we can kind of compare to batteries, where did we mark the zero voltage? At the negative or the positive end? At the negative end. And so we can do the same in batteries and call the negative end 0 volts, right? Was the positive end a higher or lower electric potential? Higher, yeah. And so we'll just arbitrarily, I love the number 8, so we'll call that 8 volts. And then electricity is coming out of it this way, right? And it asks you to label the electric potentials at each point. And so we've got point A in between the batteries, points B and C, and then points D and E. And so let's go ahead and tackle V. B and C versus D, D, and E. Which group has a higher electric potential? B and C. Why? Because they're before the resistor. Is there a voltage difference here? No, and so we can say B equals C, and then those are greater than D and E. For D and E, is there a voltage difference between those 2 points? No, there's not. And so D, which equals E. But where does A fall in between those? Mm-hmm. Good question. So when we have batteries together, we know we add them, right? Like if I've got these two and they're each 1.5 volts, what is my total voltage? 3, right? That's my total voltage difference. And so it would be like going from 0 to 3. But if I'm right here at the edge of that first battery, what is my voltage difference there? It's 1.5, right? And so then how does this value compare to the total that's coming out of both of those batteries? It's less than that, right? And so B and C are greater than A, but A is greater than D and E. And so for 31, you're looking at the picture on the right above it, and it says it's a current versus potential difference graph. What is the resistance based on the graph? And so what do I know resistance is equal to? If I were to rearrange Ohm's law. Mm-hmm. And so how can I go about solving that problem? Yeah, I could just pick one point that the line is on. Gabe, what point did you pick? 50 and 1. Yep, that's an easy one. The other way that we typically say this, and if you look on your formula sheet, it's got it for you. Resistance, when I'm looking at a graph, is equal to what? Using that formula sheet. It is. So, on this page of your formula sheet? No, find the graph. As the inverse of the slope. Right. Which equals 1 over rise over run. And then when I take the inverse of that, it's run over rise, which then equates out, okay, I've got volts over current. Right, 33. For 33, what two things have they given me? The length of the wire and the electric field. And then what are they asking me for? Delta V? And so how can I figure that out? the electric field in a resistor is equal to the voltage drop across that resistor divided by the length of that resistor. And when I set that up, what do I get? .003? 0.003 what? Volts. Somebody confirm that answer? Confirm that answer? Okay. Lisa? Good deal. Alright, questions so far? Okay. So Ohm's law, I think, is probably by far like one of the easiest things we've done. Right? It's pretty straightforward. We're gonna move into talking about power of electrical devices. What do we measure power in? Watts. Good. Did you know that from last semester or just from light bulbs? Last semester? Okay, good deal. And so this is a really brief power review from last semester. Power is a measure of how fast work gets done, right? And so if I push a shopping cart 10 meters, I do the same amount of work whether I push it in 10 seconds or 5 seconds, right? That time difference is what creates a power difference, right? The work, the force times distance is the same, no matter how fast I do it. But the power increases as my time decreases. And so it's work divided by power, work divided by time. We measure power in watts. What did we measure work in? What was it? Joules, yeah. Work is just change in energy, and we measure that in joules, and then time is in seconds. And so joules per second equals watts for us. Since work is change in energy, in this case we're talking about electric potential energy, right? The change in that energy. A charge gains energy as it moves across a voltage difference, and this is a review formula for you guys, right? That U electric is negative Q delta V, and so we gain energy as we move across a voltage difference. These two things are synonyms, and I might not have drilled it home well enough, but the potential difference of a battery has a special variable, but it's the same thing. We call it the EMF, and it's represented by an epsilon. Right, but when you see this variable, we're just talking about the voltage difference of a battery. Same thing. And so if I want to talk about power in a circuit, right, I take this formula that I already know about electric potential energy and voltage differences, and I can say it's the overall change in energy over the change in time. That's the old formula that we know for power. I can say that it is the charge times the voltage difference of the battery divided by the time. Charge over time is just current. And so I can also say that this is the electrical current flowing through something times the voltage difference. And if I wanted to express it this way instead of using epsilon, I could do that as well. A lot of variables, kind of straightforward thought process. Is that okay? This is the one you will typically use, right? And then that's related to that same question, and we're getting there. And so, let's do this first, and then we'll get to that question. Okay. So let's say we have a 60-watt light bulb and a 15,000-watt heater. I literally looked at the heater in my office, and it's got it printed. And they're both connected to standard household outlets, which are 120-volt sockets. Which device draws more current? And so those numbers, 60 watts and 15,000 watts, what are those measures of? Yeah, power. And so I'm going to solve for the light bulb first. My power equals 60 watts. Right. What else do I know about this light bulb? Yeah, delta V. It's a 120 volt socket, right? Like a 1.5 volt battery. And so I know my delta V is equal to 120 volts. And what am I asking you to find? Yeah, current for each of them. And so how can I do that? Mm-hmm. Power is equal to the current times the voltage difference. It was just that easy. So how much current does my light bulb draw? 0.5 what? Amps. Okay. And then how much current does my heater draw? Right? And so this is for the light bulb. And then can I get somebody to confirm those? Ned confirm? Gabe confirm? Light bulb was 0.5 and then heater, what'd you get, Gabe? Oh, okay. Fair enough, take your time. 125. Good. Right? And this is why when you plug in devices like heaters, because their power usage is so great, they draw a lot more current from that circuit. Yeah. Mm-hmm. Yeah, and so if you are the kind of person who uses lots and lots of extension cords, etc., right, you've got 120 volts here, you've got 120 volts here, and if I've got 8 cords coming out of that, they're all sharing that 120 volts, right? They're all sharing that 120 volts. And depending on what I plug in, that could be fine. But if I've got 8 heaters, it's not going to hold it. Right? All right. And so we get to this point of a load, and we talk about loads on circuits. A load is anything that does work with electricity. It's basically anything worth plugging into a wall or a battery. All right? What's the point of plugging something into a wall if it's not going to do some amount of work for you? Right? It's not going to go plug in potatoes in or anything. And so if it does work, then it has power. If it has power, then chances are it's a resistor. And so each one of you guys, give me an example of something that would be considered a load. Really easy, anything that uses electricity to do work. Besides the examples I have up here. It is just as easy as it sounds. TV, great. What else? Automatic door locks. Good job, Lisa. Pressure's on. Phone charger. Yeah, phone charger would work. What about those things helping you do all these calculations? Oh, they do have batteries, don't they? Okay. Thank you for being a load on that battery. And then this is the interesting relationship that Lisa's been trying to fast forward to the whole time, which is that I've got a voltage difference across a battery, right? We would say the negative terminal is 0 and the positive terminal is 1.5 volts. That voltage goes through a wire, There's no difference in that wire. None at all. It just carries that charge. But then when this current gets to a resistor, that resistor uses up all of the charge. It takes it from its high voltage to 0. It does the opposite thing that a battery does. It uses that current. And it decreases that voltage to 0. And so the power that a battery puts out is completely equivalent to the power of that resistor because it uses up what the battery puts out. Right? And because this goes back to 0 in a circuit, right? If I have this battery that is 1.5 volts, whoop, I've got my resistor, bah, bah, bah. If this is 0 going into that battery, okay, well, great. Then my battery can do its job, right? And it can step up that voltage and start it all over again. Yeah, you're kind of just shoving in what you got out of it. The battery, for other reasons, will still produce heat and it'll lose efficiency because of that, so it will kind of run out after a long time, but a lot less quickly than if you've got something that's using that electricity, right? Chances are it'll overheat, actually, probably before it runs out. And so the equations for the power of a battery are very similar to the equations for power of a resistor because they are the same power. The only difference here is that resistors have to obey Ohm's law, which is that current equals the change in voltage over the resistance of whatever that resistor is. And so I take Ohm's law and I can substitute into this initial equation, right? And I can get a lot of variations out of that. And so if I want to calculate the power of a resistor, I can use any combination of current and voltage difference and resistance that I have in order to do that through substitution. Right? I've just taken this formula, solved for either V or I, and substituted in those variables. Okay? So on page 736, try number 37 and 39. And so your homework for the remainder of the chapter is here. I do have the examples that we have already done in there, and so you've already done part of your homework. I'll give you a quiz on Wednesday. That quiz is due on Friday. You will still have your homework quiz and your lab due on Sunday. Chapter 23, we're going to spend 3 lectures on, so this Wednesday, this Friday, and next Monday. Next Wednesday we'll have a review, and then next Friday we'll have a test.